So our final speaker of the afternoon is Dr. Hans Stein. Hans is a professor of nutrition at the University of Illinois. He's internationally recognized for his work in feed ingredient evaluation, nutrient digestibility, and nutrient requirements in pigs. He has a very active research program that currently includes 8 PhD students, 3 technicians, and 2 visiting scholars. Hans is a highly sought-after speaker worldwide, so we're very fortunate to have him here today to present some information on calcium digestibility and calcium requirements in the pigs. Thank you, Hans.
Thank you for the invitation and thank you for the introduction, Alan. What I'll try to do here today is talk about some studies we have done over the last few years to look at calcium digestibility and requirements in pigs. And the take-home message is, I hope you'll leave it from here, is here. First, I'll try to convince you that phytase does increase not only phosphorus digestibility but also calcium digestibility. So I hope you will be convinced about that. Secondly, we also have data from several studies indicating calcium is not only stored in the bones. Okay, so if you've read a textbook saying 96 to 99% of all calcium is stored in the bones, we cannot repeat that. We cannot prove that. We see much greater total retention of calcium than what we can see in the bones. So that's the second thing. Third, mineral absorption is not, or calcium absorption from the intestines is not very highly regulated. It's very minimal. You feed small amount of calcium or high amount of calcium, you have very little regulation in the intestines. Okay, the regulation is in the kidneys. It's not in the intestines. And finally, excess concentrations of dietary calcium is detrimental to average daily feed intake, average daily gain, and gain to feed. Okay, so those are the 4 things I hope you will take away from this today, and I'll try to present data here that gets you to those conclusions. Okay, first, if you look at the requirements of calcium, and we have that here just an example from 100 to 125 kilogram pig. If you look into NRC, you'll see total calcium requirement is 0.46, and then the requirement for phosphorus is expressed as standardized total tract digestible phosphorus at 0.21. And you could ask, how did NRC come up with this? Well, it's described in the document how they did it. We started out with body protein, estimate of body protein in the pig. From there, the total amount of body phosphorus was calculated because there's a linear relationship between total body protein and total body phosphorus. So we could calculate phosphorus from the protein in the body. From the phosphorus mass via assumed efficiencies of phosphorus deposition, we calculated the requirement for STD phosphorus. And then from there, because there were very few data on calcium, we just assumed fixed ratios between total tract digestible phosphorus and total calcium requirements. So we simply, for a growing pig, we just multiplied this value by 2.15 to derive total calcium requirement. And so if you take this number and multiply it by 2.15, you should get this number. Okay, so that's where NRC got the calcium requirements from. Okay, whether you believe in the NRC book or not, you have to admit it was an amazingly good-looking committee, right? But when we talk about this calcium here, the committee also stated that because of this lack of data, the calcium requirements were derived simply and directly from the phosphorus requirements using unique and fixed ratios between standardized total tract digestible phosphorus and total calcium requirements for growing finishing pigs, sows, gesting sows, and lactating sows. That's what I just showed you before, the fixed ratios. However, they continued here, a preferred ratio would have been a ratio between digestible calcium and digestible phosphorus. But again, because of lack of data, the ratios between total calcium and digestible phosphorus are used. So that's what was the state of the situation 5-6 years ago when the committee looked into the literature here. We only had the total calcium requirements. So realizing that, at that point, we started doing some work on calcium and tried to address some of these deficiencies here. And we recruited 2 PhD students, and the first one, both of them finished this spring. The first one is Dr. Caroline Gonzalez-Vega. She's here today, and Caroline was with us for 5 years and finished in the spring, has done a lot of this work. And we also had Dr. Laura Merriman, who also finished this spring, and she also worked on calcium. So we had 2 PhD dissertations completed this spring on calcium, and we actually have just recruited 2 new students to continue this type of work. So what did we do? Well, we started out with some questions and say, what do we know about calcium? What is it we don't know? The first thing we asked, when we measure calcium digestibility, should it be duodenal digestibility, should it be small intestinal digestibility, or total tract digestibility? That's one set of questions. Next one was, do we have endogenous losses of calcium from the intestinal tract like we do for amino acids and many other nutrients? We've seen that for phosphorus also. We didn't know that. So that was another question we had to ask. Third was, what is the influence of phytate? What is the influence of phytase? What is the influence of fiber? What is the influence of fat and other things, particle size and other things we have looked at? So this is kind of where we started out. And I will not go through all of these things, but I'll show a few highlights, okay? So the first thing was, should we do duodenal, ileal, or total tract digestibility? We designed an experiment with that. We put 2 cannulas in the pig here, one in the duodenum, right after the stomach, and one in the ileum. And then, of course, we could collect feces also, so we could compartmentalize absorption of calcium in these pigs to see what is absorbed in the stomach, what is absorbed in the small intestine, what is absorbed in the large intestine, and what is absorbed over the total tract. I'll not show you any data on this. We did publish a paper on this, but the conclusion from that work was we might as well measure total tract digestibility because there's no difference between ileal digestibility and total tract digestibility. So we might as well do total tract digestibility because it's easier, so then we don't have to cannulate pigs. So we do total tract digestibility from now on, okay? That's what we did there. Then the next question was endogenous losses, okay? And you have a pig here, and if you try to imagine that the orange balls that are coming up here in a little while are nutrients from the feed or calcium from the feed, and the blue ones are nutrients from endogenous origin, so they're coming into the intestinal tract from different places here. Then try to follow the orange and the blue dots you see now. The orange ones are the feed, the blue ones that are coming in different points are endogenous losses. They'll go through the digestive tract. Most of it will be absorbed here in the small intestine, and there's no absorption in the large intestine, so if it's not absorbed at the end of the ileum, it will end up in the feces, right? The important thing here is this is not different from other nutrients, except you'll see that we have both blue and orange balls here. Right? That means when we take a fecal sample, you have both diet calcium and you have endogenous calcium there. So if you calculate digestibility based on intake from the feed, and then you subtract what comes out in the feces here, you get a mixture in the feces of endogenous and diet calcium. That's what we call apparent standardized total tract digestibility. But that will include this endogenous losses. So knowing that, we started out to conduct an experiment with canola meal. The reason we used canola meal is one of the few plant ingredients that have high calcium. So we had 8 diets. We had calcium from canola meal without phytase and calcium with canola meal from phytase, canola meal with phytase. And in this case, we used Quantum Blue from AB Vista. Had 4 diets, and we simply designed those 4 diets by having more calcium in the diets by adding more canola meal. That was the only source of calcium in the diets. So 0.08, 0.16, 0.24, and 0.32% without phytase, with phytase. Then we measured digestibility in these 8 diets. Here are some data. We have the orange line is the diets without phytase, the blue lines, diets with phytase, okay? And if you look at the statistics, we have the calcium level here, we have the 4 different calcium levels on the x-axis here, and you'll see that is significant here, indicating that the more calcium we have in the diet, the greater is the digestibility, okay? And you will also see that the blue line is greater than the orange line here, and that means phytase is significant. So you have a greater digestibility if you have phytase in the diet than if you have no phytase in the diet, right? So that was answering one of the questions we started out with. Does phytase affect calcium digestibility? Here you can clearly see a greater digestibility if we have phytase in this canola meal diet than if we don't have phytase there. However, this thing that calcium level affects digestibility is kind of troubling, because if you ask what is the digestibility of calcium in canola meal, you have to answer, well, it depends on how much canola meal you have in the diet. That's not very easy to use if you formulate that diet. So the reason we have this occurring here is because of those endogenous losses. Because at a low level of calcium in the diet, those blue balls I showed before, the endogenous calcium is a relatively high concentration of the total output. That means you get a low calculated value for digestibility. If you add more calcium, then those endogenous losses is a smaller percentage of total output, meaning we calculate a greater digestibility. So that's why the apparent total tract digestibility values are influenced by the level of calcium here. That's not very convenient, so we have to get rid of that and do something else. And in this case, we try to do total tract digestibility, and by doing total tract digestibility, we corrected for those endogenous losses. We took the endogenous losses out of the equation and removed them from the calculation, and only look at what is the digestibility of the diet calcium. And now you can see there's no significant effect. In fact, you have the calcium here. It's not significant. The p-value is 0.86. There's still a significant phytase effect, indicating that phytase does increase digestibility of calcium in canola meal, but there's no calcium effect anymore. So here we see clearly we should use true digestibility or standardized digestibility, so we have standardized for the endogenous losses, right? So that's answering the next question, that we should use standardized total tract digestibility to determine calcium digestibility in feed ingredients. Okay, here's another experiment we conducted a few years earlier. This is another phytase. This is the DSM phytase, and this was again looking at actually for phosphorus digestibility, but we also calculate digestibility of calcium, and this is ATTD values. We had the same amount of calcium in all diets, but different amounts of phytase. And you see the 5 diets here. As we increased phytase in the diet from no phytase to 500 units to 1,000 units, we got a break point here at a little over 1,000 units for calcium. Now, when you think about this is corn soybean meal diets. Think about corn soybean meal diet. There's no calcium from corn. There's a little bit of calcium from soybean meal, but that calcium from soybean meal could not explain this increase here. So the only reason you see this increase in digestibility in a corn soybean meal diet is that some of the calcium from limestone or calcium carbonate had increased digestibility. So now I'm telling you, phytase increases digestibility of calcium from limestone. Okay, and that may not sound very logic, but if you look at it, what happens is you have a corn soybean meal diet here with phytate in the corn. You have the limestone or calcium carbonate or calcium phosphates here with calcium, and then when they get together, that calcium from the limestone or the calcium phosphates may be bound in phytate. So that was our hypothesis. That was the only way we could explain that increase in calcium digestibility used by phytase. So conducted some studies to look at that. Looked at calcium supplements. Here we have monocalcium phosphate, dicalcium phosphate, and calcium carbonate. Orange bars, no phytase, blue bars with phytase. And you'll see for the 2 calcium phosphates, there's absolutely no difference between no phytase and phytase. But for calcium carbonate, we see a significant improvement in digestibility when we add phytase to the diet. So phytase increases digestibility of calcium not only from the plant ingredients, but also from calcium carbonate. Okay, because that calcium from calcium carbonate can bind to the phytate in the diet. Okay. Fish meal, there's no phytate in fish meal either, but same thing. We see an increase when we add phytase to fish meal in calcium digestibility. The reason again is that the calcium from fish meal can bind to phytate in the diet. So that's where we got this increase from. So phytase influences calcium digestibility again. Knowing that, we had determined digestibility values in inorganic calcium sources. We have all those values. They are in the proceedings, so if you need them, you can look at them there, both without and with phytase. We have determined digestibility of calcium in most plant ingredients that contain calcium, not all, but most of them. And we have determined digestibility of calcium in animal proteins, and so we have all those diets. So if you take all that together, what does that mean? Well, it means that we can actually use standardized total tract digestibility in diet formulation. Right, so now we can formulate diets based on digestible calcium, not total calcium, as was explained in the NRC. So we set out to do that. And we tried to see, can we determine the requirement for digestible calcium for 11 to 25 kilogram pigs. We formulated 6 diets based on standardized digestible calcium, 0.32, 0.40, 48, 56, 64, and 72% digestible calcium. And if you want to have the values for total calcium, they are here. And then we fed those 6 diets to pigs, 4 pigs per pen here in a nursery study from 11 to 25 kilograms. We also fed the same diet to pigs in metabolism crates, so we could measure calcium balances and retention of calcium and phosphorus and so forth. And at the end of this study, we killed 1 pig per pen to determine bone ash. So we had a lot of data here. And I'll kind of mix the data up a little bit. Start with the bone ash data. And you'll see here, we had a breakpoint at 0.48% digestible calcium in the diet. We got a classical curve here. It's not perfect, but it's okay. It's both linear and quadratic effects. See, at a low level, low bone ash, as we increase calcium, we increase the calcium in the bone, or increase bone ash, and then it flattens out here. Okay, that looks okay. Look at calcium retention. Same type of curve here. But you will see here that the breakpoint is greater, or the intersection here is greater than it was for bone ash. That means we need more calcium to maximize calcium retention in the diet. But it looks okay also. Phosphorus retention looks good as expected. It's low, going up, and flattens out here at a plateau. So that's also okay. Again, 0.48 looks good. However, when we get to average daily gain, we flip that curve, right? And you'll see the low level of calcium did not really suppress average daily gain, but if we added 2 high levels of calcium, we saw a dramatic reduction here in calcium, in average daily gain. So a high level of calcium really reduced average daily gain here. And the maximum point here was 0.54. So this did not determine the requirement for digestible calcium. This number is really what is the maximum you should have in the diet to for these pigs. Okay. Gain to feed, same type of curve, and even more dramatic. As we increase calcium in the diet, we see a sharp reduction in gain to feed here. Right? So again, you need to have not have too much in there, and the maximum here was estimated at 0.50% digestible calcium in the diet. Right? So very different curves than what you would expect for these type of studies. If you look at them, we have bone ash, bone calcium, calcium retention, and phosphorus retention. I showed you those numbers here, and if you look at the ratios, standardized total tract digestible calcium to standardized total tract digestible phosphorus, 1.33 to 1, 1.39 to 1, 1.67, and 1.33 to 1. So those would be the ratios that we had here. And if you look in the literature where people have actually killed pigs and completely analyzed what's in the body of the pig, those ratios vary between 1.20 to 1 and 1.60 to 1. So we are right in the middle of this for most of these, except for calcium retention seems to be a little bit higher. Right? So that was the 11 to 25 kilogram pig. What is happening here? Well, what we think is happening is that at a low calcium concentration, we have, this is the intestinal tract here, this is an enterocyte, so we have a nucleus, we have a vitamin D receptor here, and we have, if you have low calcium concentration, you get more vitamin D, 125 hydroxyvitamin D, which is the active form. And then if there's low concentration, that goes to the intestinal tract. That activated vitamin D will bind to the receptor going to the nucleus. Now we express more of the calcium channels here, where calcium is absorbed, more of the binding proteins we have that can transport calcium through the cell, and therefore at low calcium we see this increased expression of the calcium transport into the cell and through the cell, and it is exited on the other side here, right? And that all is okay. But what happens at high levels of calcium? Well, at high levels of calcium, you don't have the activated vitamin D, so you don't get the relocation of the receptor to the nucleus. That means you don't get extra expression of the calcium channels in on the basolateral side. You don't get more binding proteins and so forth. But if you add a lot of calcium in there, what happens is that calcium will come into the intestinal tract, and most of it will go between the cells, because high calcium will make these tight junctions permeable, and therefore you will get absorption of calcium. Although you only have a little bit going through the cell, most of it just goes between the cells. So this is called paracellular absorption, and that is why we don't really have much regulation of absorption of calcium from the intestinal tract, because if you add more calcium, it just goes between the cells. If you have low calcium, yes, you get more calcium proteins, and we actually measured that, and we determined these calcium channels here, the expression of those, and we determined the expression of the calcium binding protein, and as we increased calcium, we saw a reduction in the expression of those proteins. But because of the intercellular, paracellular absorption here, we had the same absorption. So what happened as we increased calcium in the diets? Well, we just simply had those pigs absorbing more calcium. So you'll see there's a linear increase in absorbed calcium. So although at the end, as you saw, these levels of calcium really reduced daily gain, it didn't reduce absorption rate. There was a linear increase in absorption. So what I said before, there's really not much regulation of absorption of calcium in the intestinal tract. Now, if the pig absorbs all this calcium and doesn't need it, what happens? Well, it goes to the kidneys. And the kidneys, they also regulate calcium. And here, the yellow lines here, or tubes, is going into the urinary tract. And you'll see they are closely associated with arteries in some parts. In particular here in the distal tubules, we have a lot of arteries around these urine tubes, and that means that there can be exchange of calcium from the urine into the bloodstream if it has to be. And if you look at these cells, they are very similar to the intestinal cells. These are epithelial cells, look exactly like the intestinal cells, except there's no villi here, but there's still calcium channel proteins that can absorb calcium. There's binding proteins that can transport the calcium through the cell, and there's exchanges on the basolateral side that can get rid of the calcium here. So at low calcium levels, you will simply absorb a lot of that calcium that otherwise would have gone to the urine, would be reabsorbed into the body, and now it can be used again. But at high calcium, you have all this calcium here. Now you get down regulation again of these proteins, so you get fewer calcium channels for absorption, fewer binding proteins. So the calcium that comes here is not absorbed. There's no paracellular absorption in the kidneys. So what happens to all this calcium? It goes into the urine. Right? And that's what the pig does to it. And therefore, you'll see as we increase calcium, urinary calcium excretion increased linearly. Right? So the regulation of calcium in the body is really in the kidneys rather than in the small intestine. Right? So that's what we concluded from this experiment. Conducted 2 more experiments. This one with 25 to 50 kilogram pigs out there. They were kind of similar, except in this case we had 20 diets because we had 5 different concentrations of digestible calcium. We had 4 different concentrations of phosphorus, so we had 20 different diets and all combinations of these levels of calcium and phosphorus. And just some brief results. Average daily gain, the red lines is the lowest concentration of phosphorus. This is well below the requirement. And you'll see the more calcium we have in the diet, the lower is the gain. A dramatic reduction here. If we had calcium at the requirement, 0.31, that's the black line, we see a reduction at the higher end here, but not as dramatic as if we have low calcium. And if we have higher calcium above the requirement, the blue or the green lines, we see a flattening out, but not as much of a negative effect. That means the negative effect of calcium and digestible of gain is at low or marginal levels of phosphorus. At high levels of phosphorus, the pigs can handle it, but not if you are at the requirement or below the requirement. Same thing for gain to feed. The red bars goes down, the black ones, the requirement, kind of flat, and the other ones flattens out at some point also here. Bone ash, same picture. We have the same form here for the low phosphorus, although we don't see the real negative effects. It's just a small quadratic response here, and we do see with higher phosphorus levels, we see more bone ash as we increase calcium, as you would expect. And retention of calcium, in much steeper curves than for bone ash. And this is where I said before, there's calcium retained in the body in other places than the bones. We don't know where it is, but we've seen that in several studies, that we see this much greater retention in the body compared to what we can show in the bones. Okay. The last study was from 100 to 130 kilogram pigs. Same setup, except in this case we only had 15 diets because we had 3 levels of phosphorus, we had 5 levels of calcium again, and the requirements are estimated by NRC at 0.46% total calcium, 0.21% digestible calcium, and then we had all the combinations here, so we had these 15 diets. 1 pig per pen in this study, killed 1 pig at the end for bone ash. Look here, feed intake linearly reduced as we increased calcium. And we simply modeled this, the responses here, and you'll see there's a negative here in front of the coefficient for digestible calcium. The more calcium in the diet, the lower was the feed intake. Same thing with average daily gain. Linear reduction as we increase calcium in these diets. Average daily gain, again, negative in front of calcium here. And phosphorus is not even in the equation. It's all driven by calcium. The whole response is driven by calcium here, right? We had phosphorus in the model, we had calcium by phosphorus in the model and so forth, but they were not significant. Only calcium explains these responses. And the more calcium we have in the diet, the lower is the gain. Okay. Gain to feed in this case was kind of blurry because we had different responses at different things, so we couldn't really get to an equation for that. We could not predict that from the intake of calcium or phosphorus in this case. Looking at the bone ash, we did have we could model that, and you'll see a small negative for calcium, a small negative for phosphorus, but a large positive for the calcium by phosphorus interaction, meaning that to synthesize bone ash, the pig needs both calcium and phosphorus, as you would expect. Right? So there's no surprise really here. But you will see where we saw a reduction in gain, a reduction in feed intake, we have linear increases in bone ash regardless of the phosphorus levels here, if it's low, medium, or high. As we increase calcium, we get more bone ash. Okay? So, conclusions. What we've seen is standardized total tract digestible calcium values are available for most ingredients that contain calcium. Not all, but most of them. And you have them in the proceedings, so you can look at them there, both without and with phytase. And we've seen phytase increases digestibility of calcium in many of these ingredients. Not all, but some of them. Requirement for calcium should be expressed as standardized total tract digestible calcium values, and we need more requirement data to have the full picture. We have done 3 studies, and we will do more in the future, but we need more of these data. Other conclusions. Oh, what happened here? Okay, excess calcium reduces average daily gain and gain to feed. I think you've seen that. And the most negative effects of calcium is observed is if STD phosphorus is marginal or below the requirement. At high phosphorus, if you're way above the requirement for phosphorus, it's not a problem to have high calcium. But at low or marginal levels of phosphorus, it is a problem to have too much calcium. And I think that is where we usually are. We don't overfeed calcium. And the last conclusion, requirements to maximize bone mass is greater than to maximize gain. And I think that's another important conclusion. You can maximize gain way before you maximize bone mass. Okay. What are the recommendations at this point, based on what we have here today, and this may change as we learn more. But our recommendation today, if you feed pigs less than 50 kilogram, the ratio between STD calcium and STD phosphorus should be less than 1.35 to 1. It's probably between 1 to 1 and 1.35 to 1. That will be our requirement, our estimate today. We don't have all the data to give you exact requirement, but in that ratio, if you have pigs greater than 100 kilograms, the ratio should be less than 1.1 to 1, based on our data. It's only one study, but that's the best we have at this point. And finally, if you are feeding developing gilts and boars, you may want to have greater ratios. It may slow down your gain a little bit, but you will have more bone ash. And if that's your objective in a developing gilt, to maximize bone ash, you will need to have more calcium and phosphorus in the diet. So those are the recommendations for today. Future research, as I told you, we have 2 new students who will work on this. We will try to verify the results we have in wean to finish studies, because what we've done so far have been short time studies, and we are a little bit uncertain if you feed at these requirement levels from all the way from weaning to finish, are they still the right requirements? Because it may be, in particular in those big pigs, the reason we didn't see a negative effect of low calcium, it's simply they had so much calcium stored in the bones that they could draw on that. So we want to make sure that we don't make a mistake on that. So we will do wean to finish studies within the next couple of years. We also want to verify the matrix values for microbial phytase and make sure we understand exactly how much does phytase increase digestibility of calcium. And we also want to verify that those matrix values can be used in diet calculations to get the same response based on digestible calcium as we get in diets without phytase. So that's another important thing for the future. Digestibility and requirement values for gilts and sows is something we have not worked on at all, and that is something that I think would be very exciting also, but a lot of work. So that's also in the future. So those are things we will be working on over the next few years. So with that, I want to appreciate the funding for this work has been almost exclusively from AB Vista, and that's why we have used their phytase in most of this work. And I do want to appreciate that they've been very, very good to us in terms of sponsoring these students, and they will sponsor the students in the future also. I also want to acknowledge my team of students. Great students make professors look good, and certainly I have great students, and I've been very, very blessed with great students for a long time, and this is a picture from earlier this year, so it's almost complete. If you want to learn more, we have a website, and you can go there. All our publications, all our research reports, all our podcasts and so forth is on this website here, so if you go to that, you can learn more if you have an interest. So with that, Alan, thank you very much.